In this video, we're going to discuss the first section of Chapter 7, which is all about probability. I've made some notes for you. I'll just be reviewing these here on the side until we start working on problems. And these notes that I've made are also available on Canvas. So 7a is all about the fundamentals of probability. Before we go into probability, we need to talk about two things that are really important to probability that can often get interchanged. Those two things are outcomes and events. So outcomes are the most basic possible results of observations or experiments. So for example, if you toss two coins, one possible outcome could be heads and then tails. Another possible outcome could be tails and then heads. So both of those are different outcomes for flipping a coin two times. An event, however, consists of one or more outcomes that share a property of interest. So for example, if I toss two coins and I count the number of heads, and you can see that the outcomes that I wrote down before, heads and then tails, followed by tails and heads, those represent the same event, right? One head and one tail. So if I'm not really interested in the order and I just define an event to be, I'm going to flip a coin two times, I'm going to count how many times I get heads, then there could be more than one outcome that can satisfy the criteria for that event. So here's an example. We got family outcomes and events. So just like in the heads and tail case, we're going to use B for boy and G for girl to represent the different outcomes that can happen. We're also going to assume that the probability or the likelihood of having a boy and a girl are the same. So consider families with two children. Let's list all the possible outcomes for the birth order of boys and girls. And if we were only interested in the total number of boys in the family, what are the possible events? So again, we're going to use B to represent a boy and G to represent a girl. And there are four different possible birth order outcomes. We can have a boy and then a boy and then a girl and then a boy, and then a girl and a girl. Later on, we're going to talk about if you have things that are like a 50-50 or two things that have only two outcomes, we can show how to make that distribution later on. But for now, we'll just take these four at face value. So these are the four different outcomes that can happen. And the order, of course, matters in the outcome. But suppose I define an event to say, I want to count how many boys I had. Well, now I'm looking at the number of boys, and these four different outcomes can actually be broken up into three unique events. The first event is, well, what if I get no boys? Or the second event could be, what if I get one boy? And the third event could be, what if I get two boys? And so what we can see is of those four outcomes that we had in the original example, I can break those four outcomes into three separate events. One of those outcomes represents two boys, one of those outcomes represents no boys, and two of those outcomes represent having one boy. So we go deeper into probability, and we want to talk about the properties of probability, or how we express probability. And probability is going to be the likelihood that something occurs, so the likelihood of an event happening. And we always express probability as a number between 0 and 1. We can include 0 in that calculation. We can include 1 in that calculation. A probability of 0 means that the event is impossible. There's a 0% chance of it happening. And a probability of 1 means that the event is certain, or in other words, it has a 100% chance of happening. Every other probability that we express is going to be a number between 0 and 1. If we express that probability as a decimal, we can turn that into a percentage to find out what the likelihood of that probability is, or that likelihood of that event happening. Again, the larger that probability is, the closer that number is going to be to 1. There's also a theoretical method for calculating likely outcomes. This is the way that we're going to define probability in this class for the most part. It's important to know that you can express probability both either as a fraction or as a decimal. So in step 1 for the theoretical method for counting the likely outcomes, the first thing we want to do is we want to count the number of possible outcomes. That's going to represent the denominator in our probability. And then among all those possible outcomes, we're going to count the number of the ways that an event can happen, whatever that event is that we're interested in. That's going to be the numerator. The probability is the fraction that's represented by those two values. I'll give you an example here using coins and dice. This example says, apply the theoretical method to find the probability of, part A says, getting one head when you toss two coins. So remember, we just actually went through tossing two coins in the distribution. But what I'll show you now is a nice way of writing that out. There are two outcomes for tossing the coin. Heads or tails. And we want to toss the coin 2 times. And so the exponent is going to represent the number of trials. 2 raised to the second power is 4. So that means in our example, there are 4 total outcomes. And we know that already because we looked at the previous one. So our outcomes is the base. Our number of trials is going to play the role of the exponent. And so in this case, we got 4 total outcomes. And what I want to do is I want to find a way to write out all of those outcomes. So here's what I'm going to do. I'm going to start by making columns. And I'm going to make columns with blocks of 2 first. So I'm going to make boy, boy, and then just below that with a block of 2, I'm going to make girl and girl. Think of this column right here as the first child. Then I'm going to do another one right next to it, where I make the second child. And instead of doing blocks of 2, where I do 2 B's and then 2 G's, now I'm just going to make blocks of 1. So I'm going to do B and then G, and then B and then G. And now if I look at these rows together, they give us all the different outcomes. Boy, 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 girl, girl, boy, and girl, girl. So this is how the distributions work for these kinds of problems. In the example that we were looking at here, they want us to find one head when we toss 2 coins, which is no different really than the boy-girl case, except instead I'm going to use heads and tails. So I'll call this outcome 1 for the first flip. Actually, maybe I'll call it flips. First flip and second flip. Again, because heads and tails each only have 2 outcomes, flipping a coin has 2 outcomes, and we're going to toss the coin 2 times, it's going to look very similar to the one that we just did. Instead of using B and G, now I'm going to use H for heads and T for tails. So my first flip, I'm going to make blocks of 2, heads, heads, tails, tails. The second flip, I can alternate these. Heads, tails, heads, tails. This gives us all the outcomes. Heads, 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 tails, tails, heads, and tails, tails. So now we know that the total outcomes is equal to 4. When we write out our probability, that's going to be the denominator. Now we go back to the question to find out what event they're interested in. And in this one, it says, part A, it says getting exactly one head when you toss 2 coins. So I go through my list here and I identify which one of these, of the 4, have exactly 1 heads in there. It looks like this one here and this one here. So the desired event has 2 outcomes. Therefore, the probability can be expressed as 2 over 4. 4 total ways, 2 ways that we're interested in. And we like to simplify probability. 2 over 4 is the same thing as 1/2. You may also see probability, like I mentioned before, expressed as a decimal, which we could also write as 0.5. I prefer either the fraction or the decimal representation. The second example asks us to find the theoretical method use a theoretical method to find the probability of getting a 3 when you roll a 6-sided die. So what are the outcomes? The outcomes are 1, 2, 3, 4, 5, or 6 when we roll a dice. A single die. So there are 6 total outcomes. In this problem, it asked, what's the probability of getting getting a 3 when you roll a 6-sided die? And so our total outcomes are 6. The desired outcome is a 3, and there's only one of those in our list. And so our probability would be 1 out of 6. One outcome that helps us out of 6 total outcomes. And so this is how we generate probability. The next example talks about playing card probabilities. We're going to talk more about playing cards as time goes on, particularly if I decide to ask you specific questions on playing cards. I would like to give you access to that distribution. But just so you know, there are 52 cards in a standard deck of cards. There are 4 different suits, known as hearts, spades, diamonds, and clubs. Each suit has cards for the numbers 2 through 10, plus a jack, queen, king, and ace, for a total of 13 cards in each suit. It also tells you here that hearts and diamonds are both red, spades and clubs are both black. So it says if you draw a card at random from a standard deck, what's the probability that it's a spade? So according to this distribution, we have 4 different symbols. We have hearts, we have diamonds, we have clubs, and we have spades. Sorry for my terrible pictures. Each of these have 13 different cards, 13 different members in the set. Total cards in this problem could be thought of just adding these up, or going back to the original told us that there are 52 cards in the deck. This is going to play the role of the denominator. The question again asked, if you draw a card at random from a standard deck, so the denominator is the entire deck of cards, which is 52. And then it says, what's the probability that it's a spade? Well, we know that there are 13 spades in the deck, and so we could express that probability as 13 out of 52. Your calculator can simplify this fraction to 1 out of 4. In other words, you have a 1 out of 4 chance of drawing any one of these, either heart, diamond, club, or spade, if you draw a single card out of a shuffled 52 deck. The next example really gives us an opportunity to talk about the differences more between outcomes and events. And so the next one we're going to do says, assume an equal chance of having a boy or girl at birth. What's the probability of having 2 girls and 2 boys in a family of 4 children? So again, I'd like to talk to you guys about the distribution for this. Remember that the number of outcomes that are possible for each child is 2. And how many times am I going to run through this process? I'm going to run through it 4 times because in this problem, I want to have a family of 4 children. So I need to calculate first 2 to the 4th power. It turns out 2 to the 4th power is 16. So there are 16 total outcomes. 16 different ways that I could have combinations of boys and girls if I have 4 kids. That's going to play the role of the denominator. But before we can do anything more, we need to find a way to express the numerator. So what we're going to do is we're going to write out this distribution. Because there are 16 total outcomes, my first child, the different ways of writing out how my first child could be born, I'm going to start with writing 8 boys and then 8 girls. Remember that the total outcome was 16, so I always take this number and I cut it in half so that I can write out whatever my first column is. So my first column is going to be a group of 8 followed by a group of 8. I'm going to write 8 B's here. Uh-oh, I'm going to run out of room. Let me try this again. For my first child, I'm going to have 8 boys. 8 different possible outcomes of having a boy first, I should say. 1, 2, 3, 4, 5, 6, 7, 8. Then I'm going to write out 8 girls. 1, 2, 3, 4, 5, 6, 7, 8. Sorry, I'm nearly out of room here. Let me zoom this out. That's better. I got too many G's. Then we want to write out in our second column. Remember that we made a group of 8 and then a group of 8 G's. Now I'm going to take those groups, I'm going to cut them in half. What I want to do here is I'm going to write a stack of 4 B's and then 4 G's. 4 B's, then 4 G's. Then 4 B's, then 4 G's. And that finishes the second column. And I'm going to go to the third column. For the third column, I'm going to cut this group in half as well. So just to recap, first group I made 8 and then 8. In the second group I make 4s and then 4s, blocks of 4. Now I'm going to make blocks of 2. Boy, boy, girl, girl. Boy, boy, girl, girl. Boy, boy, girl, girl. Boy, boy, girl, girl. And then lastly, I have a fourth child that I want to do. So for the fourth child, I'm making just blocks of 1. In other words, they alternate. Boy, girl, boy, girl. Boy, girl, boy, girl. All the way down the list. Now this seems a little tedious, and this example is really long. I don't think I would ask you to do a distribution of 16 like this on an exam, but it's a good practice to show you all the different ways that an outcome can happen, or that an event can happen. So if I go now, I can look at each one of these. Remember, there are a total of 16 of these rows that I have written out. And if I go across now, I can write out all the different ways that I could have children. It turns out that the first one is just 4 boys in a row. The second one is 3 boys and a girl. And so on and so forth. I'll leave it to you to write all the rest of these out. I'm going to do the same thing right now. Boy, boy, girl, boy. Boy, boy, girl, girl. Boy, girl, boy, boy. Boy, girl, boy, girl. Boy, girl, girl, boy. Boy, girl, girl, girl. Girl, boy, boy, boy. Girl, boy, boy, girl. Girl, boy. Girl, boy. Girl, boy. Girl, girl. Girl, girl, boy, boy. Girl, girl, boy, girl. 3 girls and a boy. And then lastly, all girls. Whew, that was a lot. What this does, though, is it gives me all the different ways that I could have for children. If the order matters, then this distribution is really, really important to us because what it does, it allows us to see all the different ways. And again, you could just randomly grab one. Imagine I have 3 girls and a boy, right? I should be able to find that somewhere in my list. And 3 girls and a boy happens here, and 3 girls and a boy happens here, and so on and so forth. So this is what we're going to do. We're interested in the different combinations of having girls and boys. So we'll write out on the side here, just like we have on this distribution in the chart, we have all the different scenarios. Now it may look a lot more compact if you look at the scenarios that they have here in the actual handout, But what I will say about that handout is it's really easy to lose track of some of these if you don't write them out more specifically. So I'm going to write out number of boys, we'll say, and we could have 4, we could have 3, we could have 2, we could have 1 boy, or we could have no boys. And so what I'm going to do now is I'm going to look through here and I'm going to identify how many of these satisfy all of those criteria. So number of boys for 4. There is only one way to have 4 boys. And so the probability of having 4 boys would be 1 out of all those 16. Now I'm going to look through and I'm going to find out the number of ways that I've written out 3 boys. So I go through my list and I find 3 B's. I have one here, 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 here. Looks like I found 4 of them. 1, 2, 3, 4 spots where I had 4 boys. So, I'm sorry, 4 spots where I had 3 boys. So for the 3, I'm going to write out 4 out of 16. The chances of having 4 kids and 3 of them being boys is 4 out of 16, or 1 out of 4. Now I'm looking for 2 boys, any set that has 2 B's in it. Here's one here, 2, 3, 4, 5, 6, it looks like. I found 6 of them in my set. And so the number of ways that I could have 2 boys would be 6 out of 16. The number of ways that I could have 1 boy, I'm looking through my set and I'm finding just a single B. Here's one of them. Here's another. And I have 2 more near the bottom here, for a total of 4 of them. So number of ways that I could have 1 boy, if I have 4 kids, is 4 out of 16. And then lastly, the number of ways that I have no boys is just this very last value at the very bottom, all girls. There's only one way that can happen out of 16. So what we just did here is what's called a probability distribution. We wrote out all the different ways that a probability can happen, and then on the side, we expressed our event. Our event in this case was the number of boys, and we wrote out all the different probabilities for those. You should always be able to check and make sure that if you add these values up together, that you get 16 out of 16 or 1. And the reason why is because this takes care of all the different outcomes that can happen. So adding those together should equal 100%. So we go into some more vocab now, and we talk about relative frequency. Relative frequency is another way of determining the probability, but it's an approximate method. Really what we're doing is we're just looking at empirically what's happened. So relative frequency method, or empirical method, is just looking at observational data and making a conclusion based on that. It's different than the theoretical method. Theoretical method means we're considering all possible cases. Much more robust, much better way to calculate probability. Relative frequency isn't really an exact probability. It's just telling you what's happened before. So this example that we have here just tells us we're interested in the number of heads when we toss 2 coins. So the different events could be, well, I get no heads, I could get 1 head, or I could get 2 heads. And I just wanted to do this like a bunch of times. So it looks like I repeated this 2 coin toss 100 times, and here are the results. I got 0 heads 22 times, 1 head 51 times, 2 heads 27 times. So the relative frequency for each of those is simply the number of outcomes that occurred over the total number of outcomes. So no heads occurred 22 times, so the relative frequency is 22 out of 100. The theoretical probability we could generate just like we did in the last case, where we make a probability distribution. We would see that no heads has a 25% chance, both of them being heads has a 25% chance, and some combination of heads and tails has a 50% chance. And it's really interesting when we look at the relative frequencies and the theoretical probabilities, because we can see that these numbers are not the same, right? 0 heads, we expect the probability to be 0.25, but what happened when we actually tossed the coin 100 times was we got a probability of 0.22. Now these numbers aren't the same, but you can see that these numbers are very close to one another, which means that theoretical probability tells us what we expect to happen, but relative frequency probability shows us that it doesn't have to happen that specifically, that it can vary a little bit. And over time, when we cover section 7C, you'll see that the more trials we do, the closer these numbers become to each other. So then lastly, we can talk about those, well, not lastly, but in the next part, we can talk about three approaches to finding probability. There's a theoretical probability, which we just talked about. We want to look at all possible outcomes and then figure out what is the true probability of this happening. A relative frequency probability is just based on observations or experiments. It's not a true probability, it's just showing us how many times an event occurred based on how many times we observed it. Then lastly, there's this subjective probability, which literally has no fact-based application in probability. It's just looking at things and based on your experience or your intuition, you're just throwing numbers out there. It's subjective. Here's an example. The first one says, I'm 100% certain you'll be happy with this car. Well, nobody can be 100% certain of my happiness. That's clearly a subjective probability. The next one says, based on government data, the chance of dying in an automobile accident during a 1-year period is about 1 in 8,000. So that's relative frequency probability. And the reason why is because what they did is they looked at all the automobile deaths on the road, and then they used that data to figure out what, on average, you think your probability is of dying in an automobile accident. The true probability cannot be calculated. There are certainly other variables in there that they're not taking into consideration, like do you live in a populated area? Are you a poor driver? Such things like that. Are you drinking? Are you wearing a seatbelt? So all of these things are actual facts that have to be considered to calculate the true probability. If they're just looking at random numbers between what happened and then making a conclusion, then they're really just identifying relative frequency probability. The third one says the probability of rolling a 7 with a 12-sided die is 1 in 12. That's actual probability. There could be a 12-sided die, and I haven't seen one, but I know they exist. And in that 12-sided die, each side has an equal likelihood of landing on the top. So rolling us any number, 7 or 10 or 1, would all have that same probability of 1 in 12. That's actual theoretical probability. So 2 more things we'll talk about. The probability of an event not occurring. So it's really interesting. Remember that the probability of 2 events, if they take up all of the different outcomes, I'm going to say A or B could happen. I don't know what A and B are. How about A is it rains today and B is it doesn't rain today. So A or B could happen, right? They both can't happen. Either it rains or it doesn't rain. And together they make up every possibility. In other words, the probability of A, and for now we're going to use this PR for probability. So the probability of A plus the probability of B is equal to 1. They always make up 100% of all the things that can happen. So if I'm interested in what's the probability of B, I can say that that's equal to 1 minus, if I brought this probability of A to the other side, 1 minus the probability of A. Here's an example. The probability of rain today is 40%. This means the probability of A is equal to 0.4. The probability of it not raining, then, would be 60%. Or 1 minus probability of A. 1 minus the probability of A would be the probability that it doesn't rain, which is 1 minus 0.4 equal to 0.6. So that's a good example of showing how the 1 minus rule works. When is this useful? It's really, really useful when they ask you to calculate a probability that is really complex and difficult to calculate, but the probability of it not occurring ends up being very easy to calculate. We'll see some examples later on during the homework where we really get an application of this. But for now, just keep in mind that any two outcomes, if they make up all the possible things that can happen, the two of them must add up to equal 1. Last thing we're going to do today is look at one more probability distribution. This probability distribution is for 2 dice. So making a probability distribution is something we already talked about when we did the 2-child case. And a probability distribution just represents all the possible events. We want to have ways of writing it out that are organized for us. If you didn't like my boy-girl example and you found a different way of writing all those cases out, by all means, share it with us. There's just lots of different ways of expressing all the different outcomes. What's important is making sure that you find a way that sticks for you. So we're going to do a 2 dice distribution. So suppose I have 2 dice and I roll them and I'm interested in what the top 2 numbers are. What I'm going to do for that probability is I'm going to make a chart. And in this chart, I'm going to put the numbers 1 through 6 at the top. And then I'm going to take the numbers 1 through 6 and I'm going to write them as a column along the side. And now in here, I'm going to fill out this chart by taking the number from the row and the number from the column and adding those values together. If I rolled 2 dice and both of them were 1, then I have a total of 2 facing up. If I roll a 1 and a 2, then I would end up getting a 3. And so what I'm doing in here is I'm adding the row and the column together. If I roll a 3 and a 1, it's a 4, and so on and so forth. So this first row is just 1 and whatever row is on the top. Then I go my second row, I'm adding 2 to each one of these numbers on the top. So it's going to go 3, then 4, 5, 6, 7, 8. If I roll a 6 and a 2, then I have obtained an 8. And I complete the chart. And we can see that there's only one way to roll a 12 if both of the values are 6. So the largest value I can roll is a 12. The smallest value that I can roll is a 2. Now I have this probability distribution, and I'm going to use that to write out all of the different probabilities for each of these. Notice that I had 6 numbers going this way, and I had 6 numbers going this way. So in a single dice, there are 6 outcomes. But because I'm rolling 2 of them, I'm looking at 6 raised to the second power, which is 36 total outcomes. And all 36 of those outcomes are written out here in my probability distribution. So when I write out probability for rolling a 2, 3, 4, 5, all the way to 12, the denominator should always be 36. So we'll write out all of those different outcomes. I could roll a 2, a 3, a 4, a 5, a 6, a 7, an 8, a 9, a 10, an 11, and a 12. So here are my outcomes. And now down here, I'm going to write out the probability of those outcomes. The probability for rolling a 2, there were only 1 2 in our chart, right? And only 2 happen to be right here. So probability for 2 is 1 out of 36. The probability for 3, how many 3s are in my chart? It turns out that when we divide the chart like this, that they make the similar numbers make up diagonals. So there are 2 3s in my chart. So this is going to be 2 out of 36. How many 4s do I have in my chart? You can probably see here I have 3 of them. 1, 2, 3. And so there's this pattern. 1 out of 36, 2 out of 36, 3 out of 36, keep going, 4 out of 36. What is the largest number, or the most common number that's rolled in this chart? It turns out it happens to be right along this diagonal right here. 7 is the most popular number. How many of them are there? 1, 2, 3, 4, 5, 6. So when we're generating our probability distribution down here, when we get to 7, we should have 6 out of 36. 1 out of 36, 2 out of 36, 3 out of 36, 4 out of 36, 5 out of 36. Now we're at 7. Here's the biggest one, 6 out of 36. Now, how many of them are there for 8? It starts going down. 1, 2, 3, 4. There are 5 outcomes for rolling an 8. So now it's 5 out of 36, then 4 out of 36, 3 out of 36, 2 out of 36, 1 out of 36. Again, we could take this and add all these values together to verify that they equal 1, which is exactly what we have here in table 7.3. But now that I have this probability distribution, I can answer all sorts of questions. A question could be, what's the probability I roll 2 dice and the sum is a 5? Well, I already have that number right here. It's 4 out of 36. The question could be more complicated than that, though, and this is where the benefit of having the distribution comes into play. What if the question said something like, find the probability of rolling 2 dice whose sum is greater than 9? Then I'd be looking at multiple outcomes that represent that event. That means a 10 satisfies the answer, an 11 satisfies the answer, and a 12 satisfies the answer. So I would take these probabilities that are already known and I would add those values together, since a 10 satisfies the answer, an 11 satisfies the answer, and a 12 satisfies the answer. So, for example, if I was interested in the probability of rolling 2 dice whose sum is greater than 9, it looks like I would add 1 plus 2 plus 3, I would get 6 out of 36 as the probability. So that's it for section 7A. The homework in here is going to be one of the more challenging homeworks of the semester, so I'll definitely be giving you guys some leeway, some extra time. We'll have a group chat on Friday just to kind of go over some of the questions that may pop up in my math lab. And for the lecture for 7B, I'll make sure that I open my math lab and give you guys some application of what you're seeing in the homework. So hope you all have a great day, and I'll talk to you soon.